Hello, my name is Soliman-Junior. I'm a PhD student at the University of Huddersfield, UK, and member of the Innovative Design Lab. Today, I'll be presenting a paper I wrote together with Professor Patricia Tzortzopoulos and Professor Mike Kagioglou entitled Exploring Mistake-Proofing in Healthcare Design. Many sources of information support decision-making across healthcare design. The regulatory assessment process observed in practice follows a recurrent set of steps. The building is designed, and its assessment is typically done based on design outputs, even if this represents a preliminary design stage. Non-compliances are then identified, and they either lead to redesign so they can be fixed, or to a derogation process, in which non-compliances shall be justified based on a set of criteria. This eventually also results in redesign and further implications on the project budget and increasing delays, which can lead to a negative health cost. Design outputs are typically obtained at the end of design stages. Design assessment is understood in practice as an independent and isolated process from the overall design. Non-compliances are only identified at late design stages. Redesign clearly represents rework, and the derogation process increases uncertainties, being a source of potential delays and overspendings. Hence, non-compliances represent mistakes in design, which should be ideally avoided, or at least their impacts mitigated. Automation can help in streamlining this process, and in fact, its use focused on design assessment has been a topic of research for many years. The main issue still identified in practice is related to dealing with subjective requirements, which depend on human involvement due to implicit and abstract information. In this sense, the use of hybrid approaches appears to be suitable, enable the use of degrees of automation mixed with human operations. In the context of this investigation, this is understood as design support systems, and mistake-proofing could benefit this process by helping to promote an approach focused on avoiding design mistakes rather than searching for mistakes after they are made. The aim of this paper is to explore from a theoretical perspective how existing technologies support mistake-proofing in healthcare design. This paper is part of a PhD research project that follows the design science research approach. It does not present the artifact of this research on its own, but it consists of preliminary findings based on theoretical evidence from literature. The contents of this paper have been also partially informed by empirical data from a study undertaken in collaboration with an institution responsible for primary healthcare buildings across England. The main steps of this investigation are related to identifying technologies to support healthcare building design, classifying these strategies according to the principles of mistake-proofing, and later analyzing their application. Mistakes should be prevented from manifesting at all, or if this is not possible, their impacts should be minimized after a mistake happens. This is the main reasoning underlying the 6 principles of mistake-proofing, which will be explored during this presentation. This classification is originally based on Shingo's ideas and has recently been also explored by Tommelein in the last IGLC in Ireland. We start with generative design, which is based on using artificial intelligence towards either optimization or optioneering. Design optimization aims to indicate the most suitable solution by solving problems with multiple variables and disciplines. Design optioneering, on the other hand, takes advantage of such algorithms to generate multiple design alternatives. These approaches could support mistake-proofing by eliminating the possibility of error, while human designers were to solve the same problems alone. For example, sorting the layout of floor plans based on constraint requirements of area and spatial adjacencies. Parametric modeling could prevent the occurrence of errors by applying constraints and object spatial boundaries. Constraints are already used to support modeling operations in current software, reflecting relationships between objects according to real limitations. Object space boundaries are related to the space required by objects in use, corresponding to their projection and associated space for maneuver. The use of parametric modeling could be further expanded towards embedding information from the regulatory framework into object families and building models. Moving to visual programming language tools such as Dynamo or Grasshopper, which could replace operations in a design process typically done by humans. The use of VPL tools can be associated to error-prone activities, related to repetitive operations, for example, including the same object many times in the building model and adapting different elements within the building model according to fixed parameters and constraints. Warnings and alerts could incorporate mistake proofing in a design process under two principles: facilitation, by visually flagging potential mistakes before they are made, or detection, promptly informing designers right after any mistake is detected. They also could force a complete stop in the design process by introducing compulsory constraints in the software, so errors could be corrected before advancing further. This is at the core of mistake proofing. Immersive approaches such as virtual and augmented reality could be adopted to facilitate designers' work, but also to support quick detection of mistakes. They enable evidencing contextual information about both the product and the associated process. They could provide an immersive environment, supporting human designers to better perform their operations in all stages of the design. A design assistant could facilitate the design process. It is envisioned as a constant guide, informing designers on their decision-making based on information from the regulatory framework. It should provide the right information at the exact time designers need to use it, by suggesting where, how, and why elements should be inserted during design. Moreover, Design Assistant could track decision-making by also recording where its evidence or knowledge was needed and how it influenced and modified the design, promoting continuous improvement. It could provide a platform for continuous learning from potential mistakes, improving design by also informing designers about what could have gone wrong. In situations where automated rule-checking techniques are used, they relate to the lowest levels of mistake proofing, in which errors and inconsistencies have already happened. If the use is at the end of design stages under an isolated and non-repetitive approach, it relates to the mitigation principle. On the other hand, if they are incorporated to design at different stages and performed under an iterative and continuous way, they reflect the detection principle. In current uses of automated rule checking, building models need to be exported from the native software to other applications under different file formats. This can eventually result in another error-prone situation due to missing information and conflicting files. In healthcare design, these strategies could support reducing the occurrence of non-compliances in the late stages of design. In fact, their practical adoption could reduce and potentially eliminate derogations from this process. Most of the times, their application, as discussed, represent an ideal situation. There are many limitations related to the way they could be incorporated to design operations, which still demand further exploration in practice. In design, mistake-proofing strategies often don't fit exclusively into one principle. This is due to the different ways the same technology could be used, according to different factors such as context, workflow, and the unique reasoning of every designer. It can also be difficult to determine what is a mistake in design and what is the relationship between mistakes and rework in this process. Differently from production, design is based on iterative and complex operations. Much of the potential rework can actually be the source of emergent and creative solutions. This understanding suggests that mistake proofing can assume different perspectives within the production and design domains. Mistake proofing is a key element in Lean. The technologies discussed in this paper explore jidoka in design. At the same time, they address key issues around requirement subjectivity from the automated rule-checking research. This theoretical framework demonstrates how design support systems can work as a convergent point between Lean and the issue around requirement subjectivity. It can be understood as a synergetic element between the subjectivity embedded in the regulatory framework, potentially addressed through hybrid solutions, and jidoka through mistake proofing. In both streams, this synergy relies on the interaction between humans and technologies. By presenting technologies and identifying their characteristics, benefits, limitations, and applications, there is a potential feasibility of using mistake proofing within the design domain. Our exploration of mistake proofing in design was conducted under a theoretical perspective. Thus, technologies have not been applied and validated in design practice, which represents a limitation and an indication for future research. The extent of this investigation can be explored even further with its practical application, for example to making do, because of the complexity of regulatory documents. Future impacts of mistake proofing in design can be even greater when we also incorporate different types of requirements, such as the needs from clients and other stakeholders. Findings from this study suggest that exploring mistake proofing in the design domain relies on better understanding the relationship between human designers and technologies and how they are enablers of one another. Thank you very much for your interest in my presentation. If you have any questions or comments, please feel free to email me.